All right. How is everyone doing this Thursday morning? A bunch of us took the exam last night. Let's refrain from talking about it until at least Monday because there's some people taking it over the next couple of days. Um, but hopefully on Monday, we can talk about it a little bit. Course logistics things. There is a problem set due tomorrow. Problem set four, and programming assignment due, I think, next Monday. When are grades expected for the exam? Um, once everyone has completed I would expect the grades to come out sometime next week. We're gonna try to grade things as quickly as possible. Once all the exams are in. Um, but yeah. Uh, so yeah. Problem set due tomorrow. I will release another problem set tomorrow. Um, and then programming assignment due on Monday. Uh, and just a reminder, as with the first programming assignment, um, you have the opportunity to get up to 10% extra credit if you submit a write-up to Brightspace. Um, and hopefully uh, the write-up submission thing is visible. If it's not, let me know. Um, but yeah, can the autograder score on PA1 be considered the final score for that one aside from extra credit? Yes. We're working on getting those transferred um, into Brightspace, but that should be updated in the next day or so. I believe it was out of 80 points. Yes. Yes. PA1 was out of 80. PA2 is out of 30. Okay. I think that's it for things that are due. Um, I figure today we can start talking about hash tables and hashing algorithms, hash functions, stuff like that. Maybe wrap that up by the end of the week. So talk about that today and tomorrow. And then next week we can move on to graphs. Uh, and then your third programming assignment will most likely be released next Monday. Um, and it will be about some sort of graph search thing. So um, hopefully that makes sense. Are there any questions on logistics things or content that we've covered so far, or anything else before I start talking about hashing? Yes, Robert, you have a question. Okay. Um, the consideration of speed for programming assignment two is just the fact that there is a timeout on the test cases. So if you have if you have a solution that's correct but too slow, then it'll time out on some of the larger test cases and you won't get all of the points. So you can expect PA2, the autograder, to also be the final score. The exit condition for PA2 is just whenever standard input stops. So whenever you get like an EOF on standard in. Yes, yeah, it happens to be in 30 segments. Having 80 test cases would have just taken way too long to run, and you would have had to wait like 10 minutes for a score, and that felt unreasonable. So, same grade, yeah. So it's going to be like weighted the same. It's just there's fewer test cases, so there's like it's more coarse grained. Um, yeah. Any other questions? Cool. Oh yeah, the late due date for problem set three is also on Friday. So if you haven't turned in problem set three, make sure to do that. Um, and then the regular due date for problem set four is Friday, and then the late due date for that is Wednesday. So, but yeah, honestly, submitting the naive algorithm first, just to make sure that you have, or like implementing a naive algorithm first, just so you can like test correctness is not a bad idea. Um, and then as you make optimizations, you can make sure that you haven't broken anything by comparing the output against the thing that you know works. Okay, if there's no other questions, I am going to get started with content. Okay, so today I want to talk about um, hash tables, and this includes stuff like hashing functions, collision, resolution, and probably some other things. Um, for reference, I am basically going to be going off of chapter 11 of the textbook. So if you want to follow along, or if you want to take a look at some of this after class, um, yeah, that's basically uh, what this is going to look like. So I guess the place to start is with this idea of direct addressing, right? Actually, ooh, here's the thing. I want to use an example from the exam, but I don't want to talk about the exam before everyone's taken it. I really put myself into a bind here. Maybe we can find a better example. Yeah, okay. Let's maybe let's start with like a motivating example for why you might want a hash table, right? Um, let's say you have, this is going to be kind of stupid, but hopefully it gets the point across. We'll start with the following problem. So you have an array of numbers, and I'll be more specific, an array of integers, 0 through m. And uh, with a single number repeated. How do you find the repeated number, right? So, for example, we've got like 3, 1, 2, 3, 5, 6, something like that, right? Um, all the integers here are distinct, except for there's two threes. So given this input, our algorithm should return 3, right? Because that's the number that's repeated. Um, okay. So one way to sort of do this with techniques that we've learned about already, right, is we can start by sorting the array, right? We can sort the array, and this gives us something that looks like 1, 2, 3, 3, 5, 6, right? And now we know that the repeated number is going to be like the two instances of the repeated number are going to be adjacent, right? So now we can traverse to find adjacent repeats, right? Um, the complexity of this algorithm. So first of all, this works, right? This is correct. If you think about the complexity, uh, sorting the array, if we are clever about the sorting algorithm we use, this is going to look something like n log n, right? And then traversing the array to find adjacent repeating elements is going to look something like theta of n. And so the overall complexity is going to be n log n because sorting is going to dominate, right? Does everyone buy that so far? Does everyone believe me on that? Cool. Okay. So, right. So this is an n log n algorithm for finding the single duplicate in an array. The question is, can we do better? Can we do something that's linear, right? And the answer, of course, is been told the solutions to all problems in life involve hash maps. That's actually not that far from being inaccurate. Like that's pretty true. Um, Hash maps are great. You can build a lot of stuff on top of hash maps. You can like put hash maps in a lot of different places, and they just kind of magically make things better. Um, so in particular, yes, the answer here is yes with hash maps. But let's try to build up to this, right? So one thing we might consider doing is we know, so here's like algorithm 2, right? Here's a second attempt at solving this problem. So for this, we know that uh, everything's going to be like we know that our ints are in the range 0 to m. So we can initialize a table of size m with -1, right? So here, our example here had things in the range maybe 0 to 6, right? Six was the largest number. So we can make a table of size, I guess, n+1, right? Because it's so we can start by making a table with 7 negative ones, right? And I'll do something like this. Now we can reverse the array for each number n, write it into the table at index n, right? So was it 3, 1, 2, 3, 5, 6? So we start by writing a 3, 0, 1, 2, 3, 1, 2. Now when we go to write the 3 again, or when we go to write a second 3, we notice that we already have something in that position, right? So if when you go to write the entry is already filled, return that. So maybe I can actually write this as pseudocode, right? So find duplicate given an array. We start by saying like table equals -1 times max array, and then for val in array if table val does not equal -1, return val. Otherwise, we say something like this, right? I guess if I'm writing this as Python, I don't need a semicolon. Okay. So obviously the complexity of this is if we know um, if we know what max looks like ahead of time, then this is constant. But there's a constant time O of 1 operation. But even if we don't, we can find the maximum of an array in O of n time, right? For theta of n, that's theta of n. And then on average here, we're going to have to loop through about n over 2 elements in the array. That's theta of n. And then all of our lookups are constant time, right? So this entire for loop takes theta of n time, which means the total thing is linear complexity. Yes? Do people believe me on this? Yes. Okay, excellent. Okay, so this, as it turns out, is a very, very simple kind of hash table, um, which we're going to call direct indexing or direct address, right? So actually, maybe I want to back up for a minute and say um, the idea of this algorithm is if we know something about our input, or if we know something about our data, then we want constant time lookup, right? So we want something that looks like constant time or maybe I'll say we want constant time lookup to see if a value is in a set, something that looks like constant time insertion, right? Um, see if a value is in a set, or find the value associated to a key, right? So the idea here is morally, at a high level, what we're doing is we're creating a set. We're assuming that we have a set that gives us constant time insertion and lookup, and for every um, element in our list, we check to see if it's in the set. That's constant time. If it's not, we insert it and we move on to the next one. So every element gets a constant time operation done to it, and then there's a linear number of elements, so the overall complexity is linear, right? Compare this to using something like a binary tree to insert things where, we can sort of uh, insert them dynamically and keep them in a sorted order, and so we get like logarithmic, something like log n for a BST, right? Or if we're just using an array or a linked list, we get something that looks like n for a linked list, right? So the reason hash tables are great, or hash sets or hash maps or whatever, is because if all we care about is insertion and lookup, and maybe deletion, I guess, I don't know, we can turn something that would normally be linear or logarithmic into something that's constant time, right? And that makes everything just a lot faster. So given that this is sort of what we want out of a data structure, maybe we can start to talk about what a data structure looks like that might implement these semantics, right? So the first one is this direct addressing, right? And this is going to be important because this is sort of what all other like hash functions, or what a lot of other hash table implementations are going to build up off of. So the idea behind direct addressing is we assume that our keys are integers. And actually, I want to say we assume that our keys are bounded integers. Go over the find dupe thing again. It's not making sense. Yeah, sure. So our linear time algorithm for finding a duplicate, we start with a table. We start by knowing what the maximum value in our array is, right? So it's 6. So we make a table with 7 entries, right? And then for each element in the array, we write it to that index, to the corresponding index in the table. So if we see a 2, we write it to index 2 in the table. If we see a 5, we write it to index 5 in the table, and so on. As soon as there's a duplicate, we're going to try to write something where something's already been written, right? So before we write, so for every element in the table, we check to see if the corresponding index has already been written to. If it has, we know we found a duplicate and we return it. If it hasn't, we write to that index, right? In this case, it turns out I actually don't need to keep track of the value itself because I already have the index. So I can just say something like false, right? And then if table is true, right? So if I can just say if that, then I return the value. Otherwise, I just write a true or something like that, right? And this is bad for space. Yeah. So that's actually a good point, right? So the time complexity of this is O of n. The space complexity, Aryan, since you brought it up, do you want to tell me what the space complexity is? It depends on the max, yeah. We can call it O or theta of M, right? Where M is max element in the array, right? So in in the case where this is constant, where like the size of the array, like the length of the array might change, but the maximum element won't change. Um, this is fine, right? So for example, let's say our array is an array of characters, right? There's only 128 possible characters, printable characters, right? Or we could say like alphabets, and then that's what 26 plus 26 plus 10, so there's like 60. There's like a bounded number of characters that you might care about, right? So in a situation like that, M is a constant, right? So the space complexity is always going to have a constant overhead because we could just initialize a table with like 256 entries and then just always use that, right? If if we don't have bounded values, this becomes a problem, right? So in fact, that's exactly what we say here. So for a direct addressing scheme, the keys have to be bounded integers, right? We create a table big enough to store all the keys. Insert equals or insert procedure. Maybe I'll say table key is just table at key equals true, right? Or maybe it's something like table key value. This is like table at key equals value, right? And then lookup table key. This is just going to be return table at key does not equal null, or just return table at key, right? If if we're using this as a set, then we initialize our table to some sort of like null value, maybe false or something like that, and then every time we insert a key, we write true. If we're using this as a map, like a key value pair, like a key value store, then we write the value to the corresponding key, and then we just return the value when we do a lookup, right? So in our example above, the keys were bounded integers in the range 0 to m, right? So table big enough to store the keys was a table with m plus 1 entries. And then this was exactly our insertion procedure. This was exactly our lookup procedure, right? I guess this one, because we didn't care about values, right? So I can rewrite the pseudocode from above to say something like, um, why the table has n plus 1 elements, because we zero, I mean, this is just a consequence of the fact that I've said things are in the range 0 to m. So there's m plus 1 different things. If I said it was in the range 1 to m, there could just be m elements, right? It's just off by one thing, yeah. Couldn't we do this by just inserting them all in a table of length and then checking if the last equals the current? Last equals the current. What do you mean by that? It's not sorted, no. So we could sort it first, but that gives us n log n time complexity. right? So the idea is we want to find something that's just linear instead of super linear, right? So I can rewrite the pseudocode from above to say find dupe array, and maybe I'll just take the max m as a parameter this time. I can say t equals init table for key in array if lookup t key return key, otherwise insert key into the table, right? And so this is the same code as before. It's just using lookup and insert, where lookup and insert are defined as they are here, right? A attendance poll question for your enjoyment. And we've sort of talked about this already. But the attendance poll is, why does it matter that the keys are bounded, right? So in particular, like if instead of taking a constant bound, if instead we did something um, uh, like traversing the array first to find the maximum key or something like that, right? What what problem might we run into? What effect might that have on the complexity? Why why in general? Why did I include the word bounded here in the definition? Wait, oh, there we go. Why did I include the word bounded? Explain what you mean by bounded. Yeah, I guess. Yeah, but by bounded I mean that we know, yeah, we know that it's within 0 to m, right? Like the we know that the input to the algorithm is always going to be integers within a particular range. It's not just going to be all integers. Of course, you could say that your bound is like int min to int max or something, or like negative int max to int max or something like that. But that's still a bound. So we can actually allocate the space, yeah. But remember, we could also just traverse to find the whatever the maximum value happens to be, because we know that our array is finite. Um, but that is essentially the idea, yes, because we need to be able to pre-allocate everything. Okay, I'll make a thing for this on Brightspace after class, but attendance poll. All right. So this, what case would violate the bounded thing? Oh, I mean, if we don't have a nice like um if let's say for example our uh our keys are like um maybe like distances, right? There's in general there's no nice like bound. I mean, so infinity in the array is one thing, yeah, but like I think maybe what I want to say is like everything, even if we assume that everything is finite, right? And even if we assume that our array size is finite and that all of the elements in the array are finite, um, if we don't start with some kind of nice like uh, if we don't a priori know what the maximum value is ever going to be for any run of this algorithm, then we can't really say it's bounded, right? So if my keys are characters, then I know that the maximum possible value is going to be 255, right? Because or you know, depending on how I'm encoding my characters, the maximum possible value might be something like 64, right? um, just because there's a very small number of available characters, right? Uh, maybe the idea of looking up something where keys or characters should remind you of something on the exam, but uh, you know, maybe you might think about the fact that that's the example that I wanted to use before I realized it was on the exam. Whatever. But that's the idea, right? So if we know going into it that the way in which we're applying our algorithm is only ever going to have keys coming from this particular set, like the maximum possible key we're ever going to see is the number 30 or something like that, then it's fine. But if that's not the case, if our keys could get arbitrarily high, right, across different runs of this algorithm, then we can't pre-allocate the space for it, or we can't say that we have constant space complexity because now the amount of space that we're using depends on the input. It's finite. I guess by bounded, I really mean like bounded before you start to run the algorithm. So you could, of course, you could say something like the bound is like 2 to the 31 minus 1 or something like that, right? The maximum like signed integer. But yeah, the idea of bounded is something where you already know what the maximum is, or where you know what the maximum is going to be at at any point. Okay, so as we've sort of stumbled onto here, um, the direct addressing is great if you have a bound, first of all, and the bound isn't something ridiculous, right? So if instead, um, well, let's think about like let's think about another example, right? Um, I want to find let's say a bunch of students, a bunch of Purdue students are enrolled in a class. Someone enrolled twice. Ooh, right? Um, this is sort of a more specific instance of the problem from before, because we can think of each Purdue student as being represented by their Purdue ID, and we can think of the array as representing like the list of IDs of students who are enrolled in a class, and we can find the element that shows up in this array multiple times, right? Or the element that shows up twice, right? Well, let's think about what that actually entails. Uh, First of all, the number of students in a class, I don't know, this class has like 60, right? Bigger classes go up to like 200 or 300. I mean, some a few hundred, right? Which by itself is fine. But if we think of Purdue IDs as our keys, right? If I need to create a table where like the index has to be someone's PUID, how big does this table have to be, right? Purdue ID is what, like nine digits, right? 9 digits, 10 digits. I'm going to say 9 digits, which means that the maximum possible value is uh, something on the order of, oh, mm, there's something like 1 billion possible PUIDs, right? And again, this we can store in a in a 32-bit integer. That's not a problem, right? Because int 32 goes up to like something like 2 billion. Um, but if the way I did this, or if the way I wanted to do this was first by allocating a table with something like 1 billion entries, and then using people's Purdue IDs to index into this table, right? The table itself is going to be, what is it, like, let's say 1 byte to represent whether someone's in the class or not. times 1 billion entries. So the table is going to be like 1 GB of memory, right? It's still constant. It's still constant time, or it's still constant space, but I'm allocating 1 billion entries. So I'm going to have roughly 1 GB of memory that I'm using for this table. And then there's like 60 students, right, in the class. Or worst case, maybe this is like a like freshman calc class or something like that, and there's like 300, right? So I've got 300 entries that I'm using in this table out of the 1 billion entries actually in the table, right? Which is just ridiculous, right? I'm allocating 1 GB of space to only ever use maybe 300 bytes, right? So the problem with direct addressing is sometimes bounds are too big. Okay, so I see subtract the min from every element and add it back at the end. That is very smart, right? Every Purdue ID is going to start with, well, actually, is it? I don't know enough about Purdue IDs, or I don't know enough about like how these are laid out, but there's a good chance that a lot of them, like the first character is a zero, right? Because there haven't been a billion Purdue students yet. And then the second character is either a one or a two, maybe, right? So we can subtract the min from every element and we get something that looks like 100 million instead of a billion, right? And then we subtract a fixed amount from the Purdue ID, use it to index into the table, and then when we're looking something up, we get the index and we add them in back at the end. That makes a lot of sense, right? That lets us take our table from something that looks like a billion to maybe something that looks like 100 million, right? We're only using 100 megabytes of memory instead of a gigabyte. Um, Assuming, of course, that all of our IDs are packed densely in this range, right? Like this assumes that, so can't I draw straight lines? Here we go, right? If this is 0 and this is 1 billion, right? If we've got 300 Purdue IDs and they all exist in this very, very narrow strip, if we've got something like that, then that's great. We can subtract the min, right? Shift this down to 0. Now we've got a table with just this tiny little width. We can use that, or we've got like a range of values of this tiny width. We can use that as our range of values, and then we can sort of go from there, right? We can allocate a much smaller table. We can be a lot more space efficient, right? That is a very good suggestion. However, in the real world, the Purdue IDs might be very spread out, like all over the place, right? Pretend I drew 300 lines. I don't have the time to draw 300 lines, but we might have like something here, a couple of things here, a bunch of things here, a couple of things here, a couple of things here, right? Now, subtracting the min lets us get rid of this much space, but we're still using like this much, right? We're still using a lot of space that is mostly empty, right? It's a very, very sparse table, right? But maybe we can keep playing this game, right? Maybe we can subtract them in, and then we can like uh I don't know. Maybe these are all multiples of 10, right? So then we can subtract them in, divide by 10 to compact them a little bit more, right? And so now instead of this, I get something that's like something that looks smaller, right? Maybe that's still not enough, so I can apply some other function, right? And for now, maybe I want this function to be invertible. And just sort of keep doing this until I've taken my um my set of stripes here and just like condensed them down into what I really want, which is something that looks very dense, right? Like all of the stripes sort of get squished together, right? Does this sort of make sense? Like I can maybe I apply something like uh f of n equals uh n divided by 2 plus 6 mod 3. I don't know. Yeah, we're mapping it down, right? We're coming up with some set of functions, right? Subtracting the minimum is one of them. Dividing by some common factor is one of them. There's any number of other like uh any other number of like invertible functions from integers to integers that we could apply and just try to find something that squishes this down, right? Once we've done that, let's say that let's pretend we magically know what the right thing to do here is, right? So there's some sort of like oracle that tells us this, right? And we get all of this into a function that I'm going to call h, right? So my new algorithm is uh, and let's say we get this down into a function called h, and we know that the range of h is going to land everything in 0 to m, where m is something much closer to our 300 students, right? Maybe it lands everything in the range 0 to 500, right? It's not perfect. I can't map everything into 0 to 300, but if I allocate space for 500, if I allocate 500 bytes and I use 300 of them, I'm fine with that, right? Um, So our new algorithm is p equals 500 bytes of space for for each student. We do t at whatever this function h is, h of their PUID, or I guess I want to say check, right? If t at h of PUID is set, return PUID, else set t at h of PUID, right? So assuming I somehow magically know what the right function here is, like what the right h to put in here is, um, I can do this, right? And now I only have to allocate 500 bytes because h is going to give me things in the range 0 to 500. I don't have to allocate a gigabyte of space and then waste most of it. Does that algorithm make sense to people? It's important to get a good understanding of this part because for basically the rest of this hashing module, we're going to be talking about finding good functions like this. All right, I see a couple of yeses. Any no's? Cool. All right. So um, per definition. H is a hashing function. So far, this only works with positive integers. Yes, that's correct. Right. So right now we're assuming that all of our keys are positive integers, and all our hash function is doing is taking this like enormous space of integers and trying to compress it down into um, something that we don't mind pre-allocating space for, right? Um, but that is a good point in the sense that if our key is not a positive integer, right? If, for example, our key is a string, right? We need some way of, like, at the end of the day, we need to produce a positive integer, right? Because at the end of the day, we're going to use something to index into an array, right? And the index for an array has to be a positive integer. We can't index an array with a string, right? So we need to somehow produce a positive integer. The problem is, um, and this is sort of where we'll get like we'll get into like the real depth of hashing, is there's not enough positive integers, right? So maybe I want to start by just talking about like deriving a good hash function, right? So doesn't the hash function already locate the specific PUID? So the hash function is taking a PUID as an input and mapping it into a particular index of the table, such that um, the 300 PUIDs that we have are going to get mapped down into a small region of the table so that our table doesn't have to be very big, right? So, for example, right, if our IDs were something like 500, 600, 800, 900, 1000, right? If we naively tried to do a direct addressing scheme on this, we would have to allocate a table of size 1000, right? And then we would only ever use 1, 2, 3, 4, 5 elements of this table, right? So that's bad, right? We're allocating a kilobyte of space and we're only ever writing to five bytes here, right? But if I look at this, I notice everything is a multiple of 100 and everything starts at 500, right? So I could say I could define a function h of n equals maybe um, n divided by 100 minus 5, right? And so now h of 500 is 0, h of 600 is 1, h of 800 is 3, right? H of 900 is 4, and h of 1000 is 5. So now, instead of allocating space for 1,000 entries, I only need to allocate space for 6 entries, right? And now I'm doing something that looks like 5 out of 6, right? So I'm allocating 6 bytes and using 5 of them, and that's fine, right? So that's the idea of our hash function. Or that's the idea of the hash function in this particular case, right? Is if we know something about the set of PUIDs that we're looking at, we can try to construct a function that has these nice properties. The bottleneck of hashing, finding the hash function. The thing is, I'm kind of lying here, right? Because if if you were to do this for every instance of the problem, so every time you had a student like registered twice for a class, you were to look at the set of PUIDs and try to come up with a hash function, then yes, that would be the bottleneck, right? You could find great hash functions because you have perfect information when you're doing this. Um, but finding the function itself would require probably iterating over the list of PUIDs more than once and like doing some more complicated algorithms, and so that you've thrown out all of your constant time things, right? Um, so on that note, the thing that we actually want to do is, or maybe the note to make here is like finding a new H each time is bad, right? Takes forever. So instead, we want to find some H that just works, right? Maybe I know that students tend to enroll for the same class multiple times. This is a problem that I'm going to have to keep solving. And so I want to design an H that works just in general for PUIDs. Right. Now, the trouble is how, like, what's the best I can do for this particular H, right? I could try to map this to the, I don't know, are there 40,000 people enrolled at Purdue, right? So I could map this into the range 0 to 40K, right? I think it's something like that. I don't actually know what the enrollment numbers are, and I'm not going to look it up right now. But I could try to spend a bunch of time offline, right? Like right now, maybe I spend a week in front of like a whiteboard, and I come up with a great hash function that takes Purdue IDs and maps them into the range 0 to 40K, right? So every Purdue student gets an index in this table. And then when I want to do this, I build a table with 40,000 entries, and I write to whatever 300 of them or whatever 60 of them or whatever are in this class. And um, I I find the person who's registered twice, right? This works because I only have to come up with a hash function once, and then every time I run the algorithm, I can just use that same function, right? Assuming that I can compute this function in constant time, right? But given the functions that we were looking at, that's not too big of an assumption, right? We're like adding and subtracting stuff, multiplying things, and we're doing like arithmetic on integers, so that's fine. Um, the trouble is, there's going to be a lot of instances where I've got a class with like 30 students, right? But I still have to allocate a table of 40,000 entries because my hash function might map like one of the students to 39,006, right? So I still need a table that's enormous. Not as big as a billion, of course, but something huge, right? So um, this is still not great, right? Uh, Instead, we could try to have a very simple, right? Maybe I can write like 40K is still not great for a class size of 30, not 30 factorial. Okay, so instead, let's say we come up with a simple family of functions. Uh, Functions that map the range 0 to 40K down to the range 0 to, let's say, C, where C is the class size, right? Um, I'm calling this a simple family of functions because we're going to have one of these for every time we apply the algorithm, because every time we apply the algorithm, we're going to have a potentially new class size. And so we're going to have to very quickly come up with one of these functions and apply it, right? And then our like hash tilde of PUID can just be, maybe I'll call this F. It can just be F of hash of PUID, right? So we can just kind of compose these together, right? Um, one such class of functions is we could just say mod C, right? People know what mod is, like modular arithmetic, mod C, right? Um, cool. Yeah. So this works, right? We can take our perfect Purdue ID hashing function, which takes something in the range like 1 billion and maps it down into the range 40,000. And then we can take that, mod it by our class size so that the only indices we're ever going to deal with are 0 to the class size, right? And now when we actually run our algorithm, we only need to allocate a table of size, class size, right? Um, and so we're going to get great utilization here. We're not going to waste any space. There's a problem. All right, it is 9:43, so I'm going to leave you on a cliffhanger. Um, anyone want to tell me what the problem is before we go? What's wrong with this algorithm? Remainders? Well, the remainder is what we're using, right? So if the class size is 10 and our hash function produces like 3,162, then I'm just going to use 2 as my index. Yeah, 301 and 601 would be the same. We're losing a lot of information, right? Multiple unique view IDs will map to the same index. I'm going to draw a sad face. And that is all for today. Tomorrow we'll talk about handling that problem. Cool. All right. You are all free to go. I will stick around if there's any questions, but otherwise, have a good one. I'm going to pause the recording here.